Alright, we are knee-deep, we are neck-deep in stereoisomers, in particular enantiomers, and for this video I want to show you how to identify if a carbon is a chiral center or not. And then we're going to have molecules, and we have to identify maybe multiple chiral centers. And then I'll probably have some time to contrast what the difference is between a pair of enantiomers, like my hands, versus a pair of diastereomers, which at this point we have not seen a lot of, if at all. Okay. Chiral centers, enantiomers, and diastereomers. Now, in a previous video, probably 0 to D50, I explain a couple ways to figure out if something is chiral or achiral, if an object or molecule is chiral or achiral. And the three ways were draw the mirror image, so at this point we only have one molecule, A. If you want to know if it's chiral or achiral, draw B, draw its mirror image. And if identical, then that is achiral. I know I've been using this example over and over again, but this pen cap is achiral, because if I draw the mirror image, even if I hold it like that, see, the mirror image is perfectly identical. Just take one off the page and on top of each other. This molecule is achiral because if I draw its mirror image, I could take that object, well heck, I could do it right now. I could take that molecule and put it right on top of it. So, do you see how these two are mirror images? And I take one and put it right on top of the other. Oops. Right there. So they are superimposable, totally superimposable. Even if I hold it this way, the reds, the blacks, and the whites all overlap perfectly over each other. Okay. But if they don't match, if they're not superimposable, that molecule is chiral. The other way is plane of symmetry. If molecule has a plane of symmetry, then it's also achiral. Okay, this molecule right here has a plane of symmetry because I could cut it down the middle right there. Now, if the group on the left was an ethyl, then this wouldn't have a plane of symmetry. But because you have two methyl groups, one on each side, let me hold it that way, actually. The right side mirrors the left side. So we're looking for, in this case now, a plane of symmetry. We're not drawing a mirror image. In this technique, we are looking for a plane of symmetry. The last way, and which is the main point of this video, is find a chiral center. If it has, for now we're just going to say one chiral center, because there are instances where there are two chiral centers and the molecule is achiral. But if it has one chiral center, then it is actually chiral. So what I'm saying here is that this molecule that we've established as achiral has no chiral center. Okay. And again, in this video, we're going to focus on that. So what is a chiral center? Okay, a chiral center is a tetrahedral carbon with, the textbook will say 4 different groups. I like to say 4 different paths, because we're going to have little stick figures, and we're going to ask them to walk along the molecule and see if they trace out the same path as each other or not. But if all 4 stick figures trace out a different path, then you have a chiral center. And if you have one chiral center, your molecule is chiral. Paths. Okay, so what was the example that was chiral? The example was this. So we'll go back to our alcohol. Okay, so we had this molecule here, and we said this was chiral. Actually, what I want to draw, because in a typical exam question, they'll show you a molecule with no wedges and dashes. Okay, no wedges and dashes, and they'll ask, where are the chiral carbons or the chiral centers? If it has one chiral center, then that molecule is chiral. Now, we do understand that, the enantiomer of this is the one with the dash. Okay, true. But on an exam question, they'll most likely draw everything line, and we have to find what? We have to find a carbon with 4 different paths. So if I take a look at this carbon at the very end, okay, it has 4 things attached to it because it's tetrahedral. A carbon, but it has 3 hydrogens. So that does not have 4 different paths. This carbon right here has 2 hydrogens. We have a path to the hydrogen and a path to the hydrogen. So that's not 4 different paths. This carbon all the way on the left, 3 hydrogens. That is not 4 different paths. But take a look at this one right there. I'm going to draw a hydrogen here. Okay? And I'm actually going to draw this much, much bigger. This is tricky because if I walk the path to the left, I end up on a carbon. If I walk the path to the right, I end up on carbon. But those 2 paths are not identical because this carbon can continue walking. Okay. So the idea is you try to locate a carbon that if you had 4 different people, green, pink, okay, I'm walking 1 bond away, blue, so the blue person will end up not on the hydrogen but on the oxygen, and then black. And they talk to each other. The green says, I'm on a carbon. Black says, I'm on a hydrogen. Blue says, I'm on an oxygen. The red says, well, I'm on a carbon too, green. So are we tracing out the same path? Well, the green says, well, I see around me 3 hydrogens also. The red person says, well, I see a carbon. This is a carbon that has 4 different paths, and typically you're going to indicate a chiral center with an asterisk. If it has 1 chiral center, this is chiral. And what do we know about chiral molecules? They have an enantiomer. Like my left hand has an enantiomer. It's the right hand. It's a mirror image that's not superimposable. So this molecule has an enantiomer where the mirror image is not superimposable. So it has an enantiomer. Now it's a little bit, don't overthink it. Okay, I understand that if you drew the mirror image of this, because we have no dashes and wedges indicated, that we don't really see chirality. What I'm saying is that when they draw it with all lines and you find a chiral center, you could say that that chiral center has 2 possibilities. Basically, the OH can be wedge or dash. So, from this idea that this molecule is chiral, you could say there are 2 stereoisomers. And what are the stereoisomers? The stereoisomers are these 2 molecules. And there are only 2 stereoisomers. In the previous video, I drew out spearmint. And I asked you to draw the mirror image, which is caraway seed. See, those are the 2 forms of that molecule. And if you recall, one of the molecules was called R-carvone, the other one was S-carvone, R and S. That's going to happen for these molecules that have one chiral center. We're going to draw an R form and an S form. Again, don't worry about what those two letters mean. Just understand that there are two forms of this molecule, and those two forms are enantiomers of each other. Enantiomers of each other. Okay. Now, chiral. Remember how we said this was achiral? This molecule here? Okay, let's prove that. If I have this molecule, I'm drawing it big again. Okay. And I have the same four people walk around this carbon here. So you're proposing, well, maybe this carbon is a chiral center. So you have your four people. Now the thing is, when these four people walk away from that central carbon, what do we notice? That this green person says, I am on a methyl group. I am standing on a carbon with 3 hydrogens around me. The red person says, well, I'm also standing on a carbon with 3 hydrogens around me. I understand it's not the same carbon, but it is the same type of path. So the green and the red walk the same path. This molecule has no chiral carbons. Has 0 chiral carbons. And therefore this is now achiral. So isn't that actually easier? If you're very good at picking out paths, it's actually easier than having to draw a whole mirror image. I think it's easier than trying to figure out from a flat drawing whether the molecule has a plane of symmetry, although some people are really good at that. Okay, I am better at finding carbons that have 4 different paths. Okay. Now, you have to work with your models if you're not seeing this. Okay, because if I have a ring, for instance, and I put, let's say, put a bromine here, okay, and I put a double bond right here. The first thing I would do is, for anything that's wedge and dash, okay, put in the hydrogen. Okay. We know that from our modeling that if we have a ring, if one of the substituents is wedge, the other one has to be dash, in this case, hydrogen. Does this have 4 different paths? Now, I know I'm toggling back and forth between wedge dash drawings and just drawings without wedge and dashes. I mean, we could do that. Let's draw this without wedge and dash. Okay. It actually doesn't matter because, this, even if I drew wedges and dashes here, you would still come to the same conclusion that this carbon is chiral, that it has 4 different paths. So, I mean, literally, if I look at this molecule here and I drew the hydrogen, yeah, I have 4 different paths. 1 to the oxygen, 1 to the hydrogen, 1 to the carbon that's a methyl, 1 to the carbon that's part of an ethyl. And you would mark this as a chiral center. Okay. So again, it doesn't really matter. It's just that I'm trying to prepare you for an exam question where they just draw lines. And you have to identify where all the chiral centers are. What did I do? B. And yeah, we'll draw an H here. The thing is, I think all of you can guess that that center is going to be a chiral center, that carbon. But let's prove the other ones are not. See, this carbon has 2 hydrogens. Okay, so this is not a chiral carbon. Okay, not. I keep interchanging them, chiral carbon and chiral center. It's the same thing. It's a chiral center that's the carbon, but this one is not a chiral carbon. What about this one? See, this one's not, because it only has 3 paths. See, there's only one hydrogen here. There's only one other bond. The shape defined by 3 points is flat. It's a plane. So you don't have tetrahedral. So we could even say that has 3 paths. It's not tetrahedral. Because remember, a chiral carbon or chiral center has to be a tetrahedral carbon with 4 different paths. Okay, so this is, and also this is flat, right? If your carbon is a chiral center, you have an opportunity to make it wedge and dash, and it'll be different, just like in this case, right? We chose wedge here, dash here. Those are our 2 forms of this molecule that's chiral. Yeah. So it's not tetrahedral, but also it's flat. Either you'll you don't see that right there. Either you'll learn later the geometry, but honestly, that's general chemistry. You should know that this carbon, right, has 3 areas of electron density. That's trigonoplanar. A trigonoplanar carbon cannot be a chiral center. For those of you who have more advanced books, you'll hear the word stereocenter. I'm not going to mention that here. Stereocenter is a little bit different than a chiral center. So just in case you have a more advanced textbook, a chiral center, I'm going to say all chiral centers are stereocenters. That is true. But not vice versa. I'm not going to get into it, but double bonded carbon-carbon double bonds can be stereocenters because you could have cis or trans. For a lot of people at this unit, that doesn't make any sense. Don't worry about it. We are always going to stick for this unit describing chiral centers. So that's not a chiral center. That's not a chiral center. That's not a chiral center. But also, if I have back my green and red person, because these are the 2 paths that are in question, because they both land on the carbon. So I tell them, keep walking. And they both land on the carbon with a hydrogen. So right now it seems like they're carving out identical paths. And then if they keep walking all the way around, they would actually recite to each other the same type of elements that they are walking. So this molecule has no chiral centers. When you hear the phrase no chiral centers, a flood of other information should be washing over you. If there are no chiral centers, then this molecule is achiral. If this molecule is achiral,